So the next topic, topic 12, is going to deal with permutations and combinations. And permutations and combinations are going to provide us ways for counting objects. We're going to break this actually into two videos. So the first video is going to go over the basics of permutations, the basics of combinations, and then we're going to do a second video where we look at the binomial theorem as an extension of the idea of combinations. But as a more complicated extension, we're going to take a look at that more carefully so we can do some of the derivations that we need. The basic idea behind a permutation is very simple. It's suppose you have some set of objects, and from that set of objects you're going to select a subset, and you're going to select the subset in such a way that the order of your selection matters. A simple idea would be, suppose you're constructing a phone number. So let's say you have a phone number 2756956, and these numbers, there are 7 of them here, and they're in a very specific order. And when order matters, what we're indicating is that if we take any number in that sequence, so for example the 6 and the 9, if I rewrite that as 9 and 6, and then I put 5, 6, the idea is that because these two are in a different order than these two, that this number is distinct from the other number. Sometimes when you're selecting objects, the order of selection matters, like a phone number, a social security number, a license plate number. Sometimes the order of selection doesn't matter. So for example, in the lottery drawing, the order in which the ball numbers are selected is irrelevant. As long as the lottery ticket you've purchased matches those numbers, you are a winner. So some examples. So list all possible permutations of the set ABC. So this is saying, hey, I have a set of 3 objects. I'm going to do a 3 permutation. So we're really saying list all possible 3 permutations of this set. So from the set that contains ABC, take all possible subsets that have ABC where order matters. So we can just start listing them. A, B, C. We can say, hey, I can start with an A, but I could have a C, B, so we change the order of these two. We could say, suppose our list starts with the letter B and has BAC, and of course we could change the order of those two. Or suppose it starts with a C, and we get CAB or CBC. So we see that there are 6 permutations of the letters A, B, C. And we can think back to the rule of product, and this ought to make sense. We're going to select 3 things. At each stage, we select and we reduce by 1 the number of items we get to select from. So there's a sense in which, hey, we're selecting objects without replacements. Once we've selected a letter, for example, we've used it. So when you make your first selection, you have 3 choices, and then you lose one of the choices. So if I had selected a B, now I would have only 2 choices, times, in my last step in my process, I'd only have 1 choice, so 3 times 2 times 1, or there'd be 3 factorial ways, 6 ways of arranging 3 objects if the ordering of the objects mattered. Then we could say, hey, what are the 2 permutations? Well, the 2 permutations would simply be take all possible 2 combinations, or 2 permutations. So I could do AB, AC, I could do BA, BC, I could do CA, CB. And again, if we think back to the rule of product, this makes sense. I have a 2-step process. Step 1, select a letter. Step 2, select the letter from the remaining letters. So how many choices are there? There's 3 times, I lose a choice, 2, and I still get 6, only because in the prior case, the last step I only had 1 choice. So there's a pat formula for calculating the number of r-permutations there are, and so the formula says, hey, if you are going to permute, if you're going to permute n objects r ways, or you're going to take you're going to take and form r permutations from a set that contains n objects. Here's the formula: n times n minus 1 times n minus 2. So you see that factorial thing going on, but you have to stop. You may not, unless r equals n, you're going to stop at some number prior to getting to n. And the claim is that to make this calculation, you just do n factorial divided by n minus r factorial. We want to kind of justify that, though. We don't want to take it for granted. So let's suppose you had 5 objects in a set, and you were going to do 3 permutations. So r in this case would be equal to 3. 3 permutations. So this is our r right here, and this is n. N is the number of elements in the set. N is the number of elements in the set. R is the number of items you're going to select out of that set to permute. So if you think about permuting 5 objects into 3 places, on your first choice for your 5 objects, they could be a set of 5 alphabet letters: A, B, C, D, E, 1, 2, 3, 4, 5. They could be a set of 5 alphabet letters. In your first step in your permutation process, you have 5 choices. So step 1 is pick one of these alphabet letters. Maybe you selected a C. And once you make that selection, you only have 4 choices for the next phase in your project, which is select another letter. So 5 times 4, and hey, maybe you selected a D in the next step. And then finally we have to pick our last number. So we say, hey, I only have 3 choices in step 3. So there's going to be 5 times 4 is 20, times 3 is 60 ways of doing this. So what we want to do is come up with, and who knows what we pick there, maybe an A, maybe an E. It doesn't matter. It's irrelevant what letters we actually pick. What matters is how many choices we have at each step in the process of permuting the 3 objects. And what we want is a nice shortcut formula for this. So the first thing I want to look at is think about this 3. If I do 5 minus 3, see this n minus r showing up here. If I do 5 minus 3 equals 2, that tells me how many elements are left after I've gone and selected 3 objects. So if I do 5 minus, hey, I've selected 3 objects, it tells me I have 2 left. So this number, if I do 5 minus 3, I get 2. This number's one bigger than that, right? So this number would be 5 minus, I chose 3 objects, but 5 minus 3 would be 2, and so I'd have to add 1 to get this guy, to get the 3. So right here, this is what you see going on in the formula. Hey, I had 5 times 4 times 5 minus 3 plus 1 is 3. This is to get the last position in the product that you have going on. Then the next element in line, let's say we're trying to come up with a shortcut formula. Let's say we finish it off and say, hey, what if I just did a 5 factorial here? This would be 5 times 2 times 1. So this guy was a 5 minus 3 plus 1. This guy here would be the 5 minus 3 guy. And so you could say, hey, I'm going to count this by doing 5 factorial, but I don't really have 5 factorial. I need to lose these 2 guys off the end. So if I take and divide by 2 factorial, in other words, if I have 5 times 4 times 3 times 2 times 1, if I divide this by 5 minus 3 factorial, which is just 2 factorial, 2 factorial is going to be 2 times 1, 2 times 1, and that's going to cancel off the extra that I got from doing the 5 factorial. So the idea is, if I divide by 5 minus 3 factorial on the bottom, which is just 2 factorial, representing the number of elements that were left, the 2, then I get rid of the overcount I got by doing 5 factorial, and I can have a shortcut mechanism for doing this calculation. So that's all that this is a generalization of this idea. Suppose you had a set of n objects and you're going to permute r of them. Well, you would get n times n minus 1 times n minus 2, and you'd get dot, 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 all the way down to times, and then you would get n minus r plus 1. You would get n minus r. That's how many items got used. So to get the number in the product, you'd have to add 1 to it, just like we did here. 5 minus 3 plus 1 to get the 3. And then you could say, hey, if I did n factorial, then I would continue. This would be n minus r times all the way down to 3 times 2 times 1. And you want to lose everything from here down, because this is your product rule piece. And so you would need to divide by n minus r times 3 times 2 times 1. But this right here is just n minus r factorial, and the numerator is just an n factorial. So you get n factorial divided by n minus r factorial to chop off the stuff. Chop off the stuff at the end of the factorial. To chop off the stuff at the end of the factorial. So some examples. So how many different ways are there to select 4 different players from 10 players on a team to play 4 tennis matches where the matches are ordered? So the idea here is we're playing, if I draw a picture of it, there's going to be 4 games. And your team is going to play against 4 different opponents. Opponent 1, opponent 2, opponent 3, and opponent 4. And we're going to assume these are distinct opponents. So if you have, so let's say you pick player 1. Player 1 playing opponent 1 is different than player 1 playing against opponent 2. This is a different match. Player 1 playing against opponent 3 would be a different match. Player 1 playing against player 4 would be a different match. So here we have something where the order matters. The order which we distribute a player against 4 opponents matters. Those constitute 4 distinct games. So if you have 10 players, when you pick the first player to play your opponent 1, you have 10 choices. The player who plays opponent 1 is no longer in the running to play the other 3 guys. So the second step, you have 9 choices times 8 choices times 7 choices by rule of product. The permutation formula says we can get 10 times 9 times 8 times 7 by doing 4 permutations from a set of 10 objects, by just doing 10 factorial, right? N factorial, doing 10 factorial, and then to chop off the 6 times 5 times 4 times 3 times 2 times 1, you do 10, you do n minus r, 10 minus r factorial. This gives us 10 factorial over 6 factorial. So the 6 factorial would lop off the 6 times 5 times 4 times 3 times 2 times 1 that we get from the 10 factorial. And then it's just a matter of calculating 10 factorial divided by 6 factorial. We've got a couple of choices. We could do this completely by hand by expanding out the factorial in the numerator and the denominator and multiplying things out. We could use software to do the calculation. I'm going to keep that. So we could, for example, take GeoGebra, which when you first open it, this is GeoGebra Classic 5, shows up in 2D graphing mode. So we could go into view, turn on the computer algebra system, and say, hey, I had 10 factorial, put that explanation mark on it, divided by 6 factorial, and hit enter. And it says, hey, 5,040 ways of doing it. And so we could walk in here and say, hey, there's going to be 5,040 ways of arranging those 4 games. The other way that we could do it is with a graphing calculator. So if you happen to have a graphing calculator, usually there's going to be a menu option for doing the calculation. On the TI-83, which I have open here, it should be similar on the 84. There's a math menu. If I open that math menu, I can go over to probability. And the combinations and permutations formulas are hiding in the probability menu because they are ways of counting things. And when you're doing discrete probabilities, being able to count items is critical. And you just go down to the NPR. So this requires you type the N first into the calculator. Then you do the NPR choice, menu selection. Then you type R. So I'm going to have to exit this for a second. So 10, we had 10 players. And then I can go math, over to probability, selection 2, NPR, a set of n elements doing r-permutations, and we're going to say, hey, we were picking 4 players, and I enter, and I can get my 5040 that way. Another example, suppose there are 8 people competing for gold, silver, and bronze. The winner receives gold, second place receives silver, third place receives bronze. How many ways are there to award the 3 medals? If we assume that all possible outcomes can occur, and the idea here is that it's a 3-step process: award gold, award silver, award bronze, and clearly order matters here, because if you are a person, hi, I'm a person P, P getting distributed to a gold medal is different than that person getting a silver, is a different outcome than that person getting a bronze. So this is an order matters. So you have 8 players. There's 8 people who might be winners. Once one of them is a winner, there's only 7 players left to get silver. Once somebody's earned that silver, there are only 6 players left to earn bronze. So there's 8 times 7 times 6 ways of making that happen. Or we use the permutation formula. We say, hey, we're going to take a set of 8 players, and we're going to create 3 permutations from them. So it's going to be 8 factorial over 8 minus 3 factorial, which is just 8 factorial over 5 factorial. So we could simplify this, which if we did, the 5 factorial would lop the 5 factorial off, and we would just get the 8 times 7 times 6 I got by applying the rule of product over here. Or we could go into software and do that calculation utilizing software, which I think I did earlier, and I think this came out to be 336 is what I got from that. Last example for permutation. Hey, let's say we have a salesperson, and that salesperson wants to visit 7 cities. How many ways are there to visit the 7 cities? Well, if we're thinking about it from rule of product, 1, 2, 3, 4, 5, 6, 7. There would be, I have 7 cities, so my first step is I choose which one I'm going to go to first. Now there's only 6 choices left, 5 choices left, 4 choices left, 3 choices left, 2 choices left, 1 choice left. Hey, this is just 7 factorial, which we could calculate using a calculator. From the permutation perspective, I would say, hey, I have a set of 7 objects, which are cities, and I'm going to choose all 7 of them to visit. And if I do that, I'm just going to get 7 factorial divided by n minus r, so I get 7 minus 7 factorial, which is 7 factorial over 0 factorial. And what we want to remember is that 0 factorial just equals 1. We can say it does by definition, but it's also fairly easy to justify why that definition makes sense. Nice number file video, for example, that you can watch on why 0 factorial ought to be equal to 1. So I won't recreate that there, but I'll point you in that direction. So this is just going to be 7 factorial, which if you grind that in GeoGebra, for example, let me keep those changes. If I pull GeoGebra up and I just type 7 factorial, messed that up. If I type 7 factorial, I get 5040. So this is just going to be 5040. All right, so now the idea of combinations. So combinations are what we get when the order doesn't matter. So for example, before we jump into that, combinations are lottery tickets where, hey, you pull those you pull those balls 59, 27, 34, 60, 44. When they're doing the drawing, if you have these numbers on your ticket and these are the balls that are drawn, it won't matter what order these balls are drawn. As long as you have these numbers on your ticket, you win. Order doesn't matter. Then you're working with a combination as opposed to a permutation where order doesn't matter. So that's the big difference between permutations, order matters, combinations, order doesn't matter. So if I start off with the same example that we had for permutations, except now we apply it to an R combination, this is saying choose all possible combinations of the set A that contains ABC. Or another way that we can say this is we can say 3 choose R. So the word choose is used frequently when talking about combinations. And if we're going to choose all of them, we say, hey, I have a set of 3 objects. Choose all 3 of them. Some other common notations are using C for combinations and saying 3 choose 3 like this. Or sometimes just a vertical parentheses where you put the number of elements in the set and the number you're going to choose. So in this case, it's really simple. All possible combinations of ABC is just A, B, C. Again, order doesn't matter. So for combinations, this is it. Remember with permutations, ABC was different than ACB, and was different than BAC, was different than BCA, was different from CAB, was different from CBA. But in this particular case, all of these different ways of permuting an A, a B, and a C are equivalent to just ABC. Order doesn't matter. List all possible 2 combinations. So the 2 combinations would be, hey, A could be paired with B, A could be paired with C, or B could be paired with C. We can't do B with A because B with A would be the same as A with B because order doesn't matter. So these are the possible combinations. All possible 2 combinations from this set. Well, AB, AC, AD, trying to be systematic about it. B could pair with C, B could pair with D, and C could pair with D. So those are all the possible combinations. And of course what we want is an efficient way to count the number of combinations without having to do what I did here where I listed the combinations explicitly. We don't want to have to list them and then count them, especially if we have a set that contains many objects. Hey, my set has 200 objects and I'm going to select 10. I don't want to list all possible 10 combinations that can be done from 100 objects. So we want to develop a formula for counting. So the formula is n choose r, or n choose r, is equal to n factorial divided by r factorial times n minus r factorial. And what you want to recognize when you see this formula is that right here is the formula for permutations. And then there's this tweak factor divided by r factorial. And the idea is that because order doesn't matter, if you calculate the number of permutations there are, a number of r permutations there are, there's an overcount if you're thinking of in terms of combinations where order doesn't matter. So thinking through simple example again where we have, let's say, A, B, C, D, E. Let's say we want the number of 3 combinations that we can get from this set of 5 objects. In other words, we want to do C and we want 5 choose 3. And here's the basic idea. So you could say, hey, I'm going to pick my objects. Well, how many do I have to choose from? I can choose 5. Next, I'll lose one of them. The next step I can choose 4. And the next step I'll have 3 to choose from. 5 times 4 times 3. We recognized from the just a while ago that we could calculate this by doing 5 factorial and then dividing by 2 factorial to get rid of the 2 times 1 that would get tacked onto the end by doing the 5 factorial. And so let's say we chose B, C, and E. Let's say we did choose B, C, and E. And what we can ask is, how many permutations are there? Permutations. Because I just calculated permutations here. What are the number of permutations? Well, when you get 3 objects, right, you get BCE, you could get BEC, you could have CBE, CEB, you could have, it could start with an E, EBC, ECB. Here's your combination, or permutations, and you can see there's 6 of them. And the idea is that 1, 2, 3, 4, 5, 6, these 6 items correspond to only one item, BCE. So there's an overcount 6 times too many when we calculate the number of permutations. We get 6 times too many. Well, this really is just a number of ways you can permute 3 things. There are 3 factorial ways to permute 3 items, 3 times 2 times 1. So you divide by 3 factorial to get rid of the overcount. There were 6 times too many permutations. So we get rid of the overcount by dividing by 3 factorial. So that's all that's going on. To calculate the number of combinations, we calculate with the big circle here the number of permutations there are, and then we recognize that those R elements can be, permuted r factorial ways. So the number of permutations is r factorial times too big if we're just counting combinations. So we divide out by r factorial to get rid of the overcount that happens. This overcount has to be accounted for. So it's always the number of permutations divided by how large the overcount was to reduce it. It turns out when you're working with combinations that if you have n objects and you choose r of them, that you get exactly the same thing if you have n elements and you choose n minus r of them. So a quick justification for this claim, and we'll need this claim in a little while. So C n choose r. Well, the formula says, hey, do n factorial. Divide n factorial by r factorial. There's where you get rid of the overcount, times n minus r factorial, so the number of permutations divided by the overcount. If instead we had C of n choose n minus r, we would just apply the factorial function to this. It'd say, hey, it's going to be n factorial. And then to get rid of the overcount, we take the thing in this position. We do n minus r factorial times, and then just like we did up here, n minus r factorial goes next. So it's going to be n minus the thing in the second position, n minus r factorial. And then we simplify this a hair. We get n factorial divided by n minus r factorial. And we get n minus n. Right, we get n minus n plus r when we distribute the minus sign in, which simplifies to n factorial divided by n minus r factorial, and this simplifies to just r factorial. And we recognize that the denominators are the same because multiplication is commutative. The order of multiplication doesn't matter. So some examples of calculating combinations. So how many ways are there to select 5 starters for a basketball team if the team has 10 members on the team? So again, in this case, we'd be ignoring positions on the team and just thinking about, hey, how many ways are there to have 5 starting players on the floor? So we don't discriminate. Hey, if I choose Paul first and then Bob, that's different than if I choose Bob first and then Paul. This is an order, doesn't matter. I've got 5 players on the floor, it doesn't matter what order you say their names in. So we're going to do 10 players on the team. We're choosing 5 of those players. So it's going to be 10 factorial divided by 10 minus 5 factorial would be the number of number of ways of permuting 5 players. We would divide by 5 factorial, by r factorial, to get rid of the overcount. And this is just going to simplify to 10 factorial over 5 factorial times 5 factorial. And we either calculate this using software. We either calculate it using software. So for example, I could open GeoGebra. I could say, hey, 10 factorial divided by 5 factorial divided by 5 factorial is 252. That would be one way to do it. So I get 252. Put that over here. We could do it using the graphing calculator. I could say, hey, in my graphing calculator, let me keep those. In my graphing calculator, I'm going to go into the menu. I'm saying I have 10 players on my team. And from those 10 players, I'm going to choose a subset of size 5. So I go over to my probability menu. That wasn't what I wanted, so I'm going to clear that. I got my 10 players on my team. Hit the math menu, go over to the probability menu, down to the NCR, which is N choose R. There's my combinations. I hit enter. I say, hey, I'm choosing 5 players to play. Enter. There's my 252 possible player combinations that I could start on the floor. Or we could hand calculate it if we wanted to. We could recognize that this 5 factorial here is going to get rid of 5 factorial off of the 10, which would leave us with 10 times 9 times 8 times 7 times 6. This 5 factorial would cancel the 5 times 4 times 3 times 2 times 1. That comes from doing 10 factorial. And then we would still have another 5 factorial left over, which is 5 times 4 times 3 times 2 times 1. And then we could start simplifying, which is kind of fun to do. 3 times 2 is 6. Goes into 6 once, so we would get what? 9 times 2 times 2 times 7, which we know is going to come out to be 252 without even doing the work. Next example takes the rule of product and applies it at the same time as applying combination. So it says, in how many ways are there to select a committee to develop a discrete math course? So we're going to make a committee of people to construct a course. And the committee has to have 3 math faculty, 2 computer science faculty, drawing from 7 math faculty, and 5 computer science faculties. This is going to be a 2-step process, which is going to make it a rule of product. So phase 1 is going to be select a math faculty, select the math faculty component of the committee, and then phase 2 is going to be select the computer science component of the faculty. So first, how many ways can we construct our math subcommittee? And there are 7 faculty to choose from, and we're going to choose 3. We have 7 faculty to choose from, and we're going to choose 3. And then times, in phase 2, we select the computer science faculty, so there are 5 to choose from, and we need to choose 2 of those 5. So we get 7 choose 5 in phase 1. Rule of product says multiply it by the number of choices in phase 2, which is 5 choose 3. So we're going to get from 7 choose 3, we get 7 factorial divided by 3 factorial times 7 minus 3 factorial. And then phase 2, we get 5 factorial. We're choosing from a set of 5 divided by 2 factorial, getting rid of the overcount, times 5 minus 2 factorial. So we get 7 factorial over 3 factorial times 4 factorial times 5 factorial over 2 factorial times 3 factorial. And then we have to make a choice. Are we going to do it by hand? Are we going to do it using software? If we do it by hand, The 4 factorial here, if I pick the bigger of the two factorials, the 4 factorial will cancel 4 factorial off the 7 factorial, which will leave me with 7 times 6 times 5. 7 times 6 times 5 divided by the 3 factorial that's still there, so 3 times 2 times 5 factorial. We'll have 3 factorial canceled from it, which will leave 5 times 4. 5 times 4 divided by 2 times 1. And then we can kind of simplify things. 3 times 2 will go into 6 once. 2 will go into 4 twice. And we get 5 times 2 is 10. Times 7 is 70. Times 5 is 350 ways of constructing this committee.